Hi, everyone. Thanks for coming to our talk. My name is Robert. I'm joined by my colleague Lanting, and we're going to talk about Ray's adoption at Robinhood and how we use KubeRay to build a distributed ML training platform on Kubernetes. So the agenda for this talk will first go through some of the context on the previous version of Robinhood's ML training infra prior to adopting multi-node training. Then we'll get into some of the limitations that we faced for our machine learning engineers and data scientists on single node training and why we decided to adopt Ray and KubeRay as our means of deploying Ray clusters. Finally, we'll get into some of the integrations with KubeRay and Robinhood's Kubernetes infrastructure that we've built. So a note on our team, we're part of the AI infrastructure team at Robinhood, one part of which is managing the ML platform used by our data scientists and ML engineers. This consists of several components, namely our notebook solution for exploratory data analysis, the model training platform, which is the main focus of this talk. Our internal model training platform is called King's Cross. We also manage other steps of the ML lifecycle, such as model serving and online feature store. In addition, our team manages some of the core AI infrastructure, and we're part of a larger AI org in Robinhood that's responsible for AI and ML platform development. Now I'll give some quick notes on ML infra at Robinhood and some of the things that make it a little bit different than other companies. So in terms of the modeling frameworks that we use, we focus on two main modeling frameworks. We use primarily XGBoost for our gradient boosted decision tree models, and for all of our deep learning use cases, we've consolidated on PyTorch. Being a financial firm, security is a top consideration for us, and many of our use cases involve personal and financial data. As part of this, we want to have a least privilege requirement where we ensure that models are only trained on data that they've been or that is acceptable for that use case. We also want to avoid things like local data access, and we want to ensure that there's auditability for all of the training jobs and the model artifacts that get used in production. And to give some examples of the types of ML use cases we have at Robinhood, a big portion of our use cases are fraud. Then we also have things related to cross-selling Robinhood's expanding product suite and various applications related to our credit card offering. Next, I'll go through what our training job creation process looked like prior to adopting KubeRay. So for all of our training job runs on the cloud, there are essentially three high-level stages. First, the model developer will write their training code locally or in their IDE, in their IDE or like editor of choice, and then their job gets packaged up and deployed onto our cloud compute, which has access to large nodes and GPUs. These jobs are also deployed in our corporate VPC, which grants them access to all the data that they need for training the model. And finally, users can monitor their job status, logs, and metrics using tools like Grafana and MLflow. And now I'll dig a little bit deeper into that for what the ad hoc development flow looked like for ML model developers. As I mentioned, the user's journey starts with their local, writing their local code. And then they'll use a CLI that's part of our King's Cross platform to upload that code, package that code up and upload it to blob storage. Next, we have another CLI that they use to, as their interface for submitting a job to our ML and AI job management platform, King's Cross. Inside of the King's Cross server, we will translate this user request into a Kubernetes API call specifying information that includes like what is the user's role and the permissions that they should have to different data sources, the node class that they want for scheduling their job, and the amount of resources they want in terms of CPU, GPU, and memory. We'll also assign the job image based on one of the centralized job images that has dependencies pre-installed that our team maintains. And finally, we'll pass through all the users' train script specific arguments that they've provided. We use all this information to create a Kubernetes resource using an abstraction layer built on Kubernetes at Robinhood called Archetype. And this abstraction layer wraps around a native Kubernetes job. Inside of that job, there are two main components. We have an init container that will download all of the job code onto the pod, and a main training container that will execute the user's, the model developer's actual training logic, and in the process, write metric. We have tooling for logs, metrics, and writing out artifacts back to blob storage, as well as metrics to MLflow. And a quick note on why this worked for a while for Robinhood. So previously, most of our models were tree-based models, and the data sets were small enough that they could easily fit into a single moderately sized node. As we've developed, we've moved towards more deep learning use cases. For a long time, we also had fewer models. So this meant there was like less competition. We could reserve enough resources where having to scale up frequently wasn't as necessary. As we've adopted more deep learning, as our data sets and models have grown, this has become less true. And here I want to show some of the sample job submission requests that users use for submitting requests to the King's Cross platform. We support 3 different means of submitting jobs. For development, we have the CLI that I talked about on the last slide. We also support users submitting jobs from a Databricks notebook. And for jobs that have been productionized, we've developed a Airflow operator for managing this job submission and tracking. As you can see, like the parameters in this example are correspond to the ones I was talking about on the previous slide. What is the image that they need to use? What is the GPU type, and how many GPUs and CPU and memory, as well as the job-specific arguments. So our data scientists and ML engineers are familiar with this workflow, and it's worked for them for a while. So as we move towards multi-node training, we want to preserve the same user experience for them and not require too much disruption in their workflow. And now I'll move into talking about some of the motivations that we had for doing distributed training. And we'll cover some of the main categories that I've grouped into 3 sections here. The first being job duration. So for security purposes, we limit the duration that ad hoc development jobs can run on our platform. And when this is coupled with the limits of running on a single pod, which implicitly means running on a single node, that really limits the size of the models and the size of the data sets that we can use for training. It also creates challenges for complex workflows like hyperparameter optimization required by some of our model developers. The next limitation area we have is on job size. So some of our training jobs require significant amounts of the different resource types, primarily GPU and memory. And for some jobs, this has gotten to the point of not being able to fit onto a single node. There's also the shift in the types of ML training jobs that we have from more of the tree-based to more of the deep learning architectures. And in these deep learning cases, using more GPUs can offer a lot of speed-ups by doing things like data parallel training schemes. So these things together cause a lot of contention for the GPU resources that we have among our different users on our platform. And can also, because the mix of CPU, memory, and GPU that the users need does not necessarily correspond to what's available on the nodes, it can also lead to low utilization as an issue. Finally, there's an issue of resource availability. So if we want to use the nodes that have the large GPUs on the most recent architectures, these can be pretty hard to scale up on demand. So if everyone's trying to use these nodes because their job will only fit on these nodes, then this can lead to insufficient capacity errors when trying to scale up to meet the developer demands on our platform. And one way of addressing this would be to reserve more nodes, but that has the drawback of incurring a lot more fixed costs, and it also exacerbates the low utilization issue for the GPUs. In contrast, a lot of the workloads that we have can be moved to smaller GPU nodes if we can distribute the workload across multiple nodes. So we can alleviate some of these availability issues. We also have a constraint that on which regions we can go to access the GPUs. So we can't necessarily go out to another region to find availability for these larger instances. So we need to think of how can we do these on smaller instance types. Now I'll talk a little bit about why we decided to choose Ray. One of the major benefits that we saw with Ray is that it's a very flexible, distributed platform for ML training tasks. And we serve model developers for all of the training use cases at Robinhood. So we want to make sure that our platform is flexible enough to meet all of their current and probable future use cases. Ray also has these high-level libraries for particularly like Ray data and Ray train that provide a lot of useful tools for doing things like streaming and last-mile data processing and integration with the ML frameworks that we already use at Robinhood. Further, Ray's already been adopted for some time in the single node training use cases that we had. So a lot of the jobs that users have can easily be translated to from single node distributed training to multi-node distributed training. And another benefit is that because Ray has an integrated ecosystem with both training, hyperparameter optimization, and serving, there's a lot of potential for us to have an integrated model lifecycle development experience, though currently we focus mostly on the train aspects. And now I'll hand over to my colleague Lanting to talk about KubeRay.
So we chose KubeRay specifically because Robinhood runs on Kubernetes, and we know that whatever distributed training solution we come up with, we also want it to run on Kubernetes. We don't really want to be in the business of manually creating and tearing down VMs and setting up all sorts of networking, infrastructure components, et cetera. We also have a lot of internal integrations around observability, networking, auto-scaling, et cetera, built by other infra teams that are on Kubernetes. The reason why we went with an open source component is because we would like full control over the entire lifecycle of the Ray cluster and the related infrastructure configurations. This flexibility allows us to integrate KubeRay with our existing developer infrastructure and access control mechanisms better. And because we have existing observability and some degree of GPU management infrastructure already set up that we can just augment KubeRay with, we didn't really feel like we needed to go with a vendor solution. Next, I'll talk about how we actually integrated KubeRay with our existing training job development workflow that Robert previously talked about. There were a couple of design decisions that we had to make along the way. The first is whether we want to have a long-running shared cluster that just takes job requests and runs them, or whether we want to create a new cluster for each new job run request. And we ultimately went with the latter. There are a couple of considerations here. The first is the noisy neighbor problem. Especially true during the initial development phase, users probably don't really know how many resources their jobs requires. So whatever request they put is an educated guess. We don't really want the bursty resource utilization of one job to affect the resource utilization of another. And another important consideration for us is around access control. At Robinhood, we manage access at the team and namespace level. For example, if a team's workload needs to access a specific S3 path, then we set up an IAM role that only has permission to that path, and then we tie that IAM role to a service account in the namespace that's running that workload. So by nature, namespaces are permission boundaries, and Ray clusters are also namespace scoped in Kubernetes. We let the pods in the Ray cluster mount the service accounts in the same namespace that have permissions only to the things that we expect the training job running on that cluster to need. So you can imagine if we have two different jobs from two different teams that are running on the same Ray cluster, if one team's job requires access to, let's say, another S3 path that this other team's job doesn't need, then we are going against the least privilege principle because this entire Ray cluster needs access to both teams' permissions. And the final consideration is cost. We don't really want to have idle clusters sitting around and just wasting money. So we spin up clusters whenever there's a new job, and when the job completes, we tear down the cluster. And there is a trade-off with the cold start problem where we need to wait for the new pods for the new cluster to get created and get scheduled, et cetera. But it's relatively insignificant at the moment given the time it takes to run our training jobs. And the next part that we had to figure out was how do we actually distribute the job code onto the Ray clusters. And we have two different training job flows here. One is the development flow, where the user is still playing around and testing with their training job code. So the key here is that we want to optimize for velocity. We don't really want users to have to go through code review and then run all the post-land builds and then have like an image get built in order for them to be able to get their code onto a pod. So we allow users to upload their job as a tar onto S3. This is the same as the single node training example previously. And we have an init container that downloads the code from S3 onto the pod. So in this distributed case, we have all pods in the Ray cluster run the same init container that pulls their code from S3. There are other documented solutions of how you can get the code onto the pod. You can mount the code from a config map, which is obviously not very scalable, or you can specify a working dir field using the Ray jobs API, either through the Ray job custom resource or through the Ray job submit CLI tool. We just went with the init container method because it's battle tested, we know it works. The other flow here is the production flow, which is when the user is done with testing their training job code, they're sure it works, they commit it to Git, it goes through code review, it gets landed, and there's automatic builds that builds an image that layers their training job code on top of the Ray-based image, along with their framework-specific pip dependencies. And this container image gets pulled to every pod in the Ray cluster, and that's how their job code gets there. And next, Robert will quickly talk about why we pre-install pip dependencies in the image as opposed to dynamically installing them at runtime.
So we decided to use images that have the pip dependencies pre-installed because we at Robinhood use a monorepo, and we wanted to make sure that the package versions that users are using in their jobs are compatible with the other first-party libraries that we package into our ML training platform. We also wanted a way of ensuring that developers' jobs are at least starting from a point of having the same set of dependencies that the production jobs would have, though as a means of allowing users to test out new frameworks and install requirements that they need for new use cases, we do expose a capability for them to add new dependencies and rebuild the images. Additionally, Robinhood has a policy of trying to not dynamically download and install things onto production pods. So we want to keep this consistent between development and production workflows where possible. And finally, there's also a performance aspect of this. So for startup time, because we do sometimes need to scale up new nodes and because we're creating these clusters on demand, we want to minimize the time that it takes for the pods to get ready and actually start running the training logic.
Okay, cool. Next, I will continue to talk about how we actually create the cluster of pods. So recall that a key benefit of using KubeRay is that it comes with custom resources that automate the management of a Ray cluster lifecycle. So the two custom resources that KubeRay offers are a Ray job and a Ray cluster. A Ray cluster essentially gets translated into a head node pod and optionally one or more worker node pods, depending on what you configure. By the KubeRay operator. And a Ray job gets translated into a Kubernetes native job in addition to this Ray cluster custom resource. So if you just have the Ray cluster, you will have to use other means to trigger a distributed job run on that Ray cluster, like maybe using the Ray CLI through your terminal, but this Kubernetes native job here submits that for you. But we ultimately decided to create the Kubernetes native job and the Ray cluster separately. And the reason for this decision has to do with our existing internal developer framework called Archetype. The Archetype framework consists of two custom resources. There's the application custom resource and the component custom resource. On the application level, you can configure the image hash, which maps to the version of code that you're running, and you can configure what sidecars you want to run. Some example sidecars are like Envoy or like telemetry-related sidecars. And then you can configure your level of alerting and some metadata, like who owns this application. Each application can optionally have one or more components, and on the component level, you can specify what init containers you want to run and what resources you want to request for each container, and what's the entry point command to your binary or script, whatever you're running. And a controller watches over these custom resources and creates native Kubernetes resources based on them. So if you're running a server, then likely we're creating a deployment. If you're running a ML training job like us, then a native Kubernetes job gets created. So the benefit of this framework is that we abstract away common configurations that are shared between the same types of applications. So the application owners only need to focus on what matters to their application. It also abstracts away the underlying Kubernetes layer, so people don't need to spend time understanding the different Kubernetes native objects and how to configure them. And the archetype framework comes with a nice user interface called the deploy dashboard, where users can see the status of their applications and which version their application is running currently, when it was last deployed, and access links to monitoring logs in a centralized place, so they don't have to interact with Kubernetes using kubectl, the command line tool. There's also integrations to automatically deploy new versions of their application when a new image gets built upon landing code. What this means for our production jobs is that users only need to make a job submission request once. When they subsequently edit their training job code and commit that to Git, their jobs that are running in production automatically get updated. And so going back to our decision to create the Kubernetes job and the Ray cluster separately, we wrap this Kubernetes native job within an archetype component. And so on deploy dashboard, users will be able to see links to this component's logs. What will the logs be? Well, it will be the logs from their training code, because this native Kubernetes job here, after submitting the job request to the Ray cluster, it will continuously pull the status of that submitted job, and it will continuously pull for logs from that training code. And once that training job completes, we have this Kubernetes native job exit. So when they see the status of this native Kubernetes job on the deploy dashboard, that basically is the status of their training job run. And they don't really need to be aware of this underlying Ray cluster that's running their distributed training job, other than what number of workers they want to configure and what resources they want to request. And here's a bit more detail of what that Kubernetes native job wrapped in archetype runs. So in order to submit a job request to the Ray cluster, you can either go through the Ray jobs API or use a Ray client. We found this Ray client method mentioned in a couple of companies' tech blogs, but the documentation mentions that there's architectural limitations, so we didn't pursue this. The Ray job submission Python SDK and the Ray CLI use the same Ray jobs API. We went with writing Python code just because it's more readable code. And we packaged this code into a container image, run it on the Kubernetes native job. So all in all, what this looks like is when a user makes a request to create a distributed training job, King's Cross server receives that request, and it creates a archetype wrapped Kubernetes native job and a Ray cluster. This archetyped wrapped Kubernetes native job looks for the Kubernetes native service that's backed by the Ray cluster's head node pod. And then it submits a job creation request to that Kubernetes native service. Meanwhile, the Ray cluster gets translated into head node pod, worker node pods, et cetera, by the KubeRay operator. We don't really need to worry about that. The automations that we built to enable this end-to-end flow First, we augmented the King's Cross server. Like I mentioned previously, when the user submits a request to create a distributed job, we create the Ray cluster, we create the Kubernetes native job wrapped in archetype, we get the head node's address, we pass that to this archetype wrapped Kubernetes native job so it knows where to send the request to, and we also pass along like the user's job arguments to their training code job. Job is an overloaded term. And we output monitoring links to the user. And we also had the King's Cross server be able to create Ray clusters and that Kubernetes native job wrapped in archetype in 2 different Kubernetes environments that are completely isolated. So we can isolate our production flow from our development flow, which runs non-code reviewed code. And we also built a garbage collector that periodically pulls the Kubernetes API server for all Ray clusters and their associated Kubernetes jobs that submit the job, and delete the ones whose training jobs have completed. Again, we know that the training job is completed because the Kubernetes native job that runs the job submission request has a completed status. And we delete ones that are done. The reason we have a separate garbage collection component is so that we can keep the King's Cross server stateless. Next, Robert will talk about the outcomes.
Yeah, to wrap things up, we'll talk about a couple of the outcomes we had from adopting KubeRay. First, we were able to take some of our existing training jobs, ones that were limited in how much data they could actually be trained on because of the single node limitation, and we were able to increase the trainable data set size by 7 times. We think we can actually go like well beyond this in the future. We were also able to reduce wait times for GPU resources because instead of having just like a few of the large GPU instance nodes that these large jobs have to run on, and then not necessarily being able to scale all the way up to meet demand, these jobs can be instead sent to multiple of the smaller GPU nodes that can tend to be able to auto scale more easily. And this leads to like more predictable wait times. Instead of having to wait for other users in the queue to finish, we just need to scale up the nodes. And that's the end of our talk. Thank you everyone for attending, and we have some time for Q&A.
Well done. Well done. Thank you. Questions? You look so excited. All right.
Thank you so much. It's very informative. Can I ask about the base image you mentioned in your slide, Ray base image? I just wondering, is that base image kind of released by infrastructure team? And the data scientists had to use that base image for development and productionize. Is that my understanding right?
Do you want to take this?
Yeah, the Ray-based image is the one that's released by Ray, and do they need to use it?
Sorry. Actually, we take the Ray-based image and we take like the critical aspects of it and we rebuild it using a different framework for building the container.
Okay, I have a follow-up question, right? How you guys enable the data scientists to share their knowledge then? Because if you control the base image, maybe some scripts, some data scientists or machine engineer already write, and they want to share and enable other data scientists to reuse it. Is there any process they can submit a request to build their UTL function into the base image so other ones could benefit, or actually everyone just write from scratch?
Yeah, we do maintain some like shared first-party libraries that the data scientists and MLEs can commit to our monorepo so that they can share like reuse those utilities across multiple training jobs.
Hey, I have some questions. I have 2 questions actually. First is you mentioned the cross-sell Robinhood product. What is that? I'm very sorry. I'm from Coinbase, so yeah. The next question is you're saying the jobs times are limited by security purposes. Is that like how should I understand this concern? And is that just because you can just talk to security and remove this, and you don't have to have this anymore? yeah, to try to understand this.
So cross-sell, generally that's like we have multiple products, and so we're interested in like if these users are using a particular product that Robinhood offers, like maybe they're also interested in this other set of products that Robinhood offers, and trying to like identify what those what are like the most promising things that they might be interested in. For the security part, I can't get into a whole lot of detail on like why we have the security requirements, but something that we sort of have to work around, and we're not able to just like remove the job duration limit requirement for development workflows. For production workflows, it's a different story.
How many GPUs are we talking about? Are there hundreds of GPUs, thousands of GPUs in this Ray cluster? And I have another follow-up.
For most of our jobs, they don't require that many GPUs, so we're not running like hundreds of GPU workloads. They're max in the tens for us right now for individual jobs.
A total of like how many?
Oh, for like all for across all of our users and
the entire platform. How many GPUs does it use?
At peak usage, probably around like 100 GPUs.
I see. Okay. So how big is your team?
How big is our team? So, we the AI infra team that we're on has like 10 or so people, but we're spread across like we maintain like the whole ML development life cycle, so multiple components.
Yeah, of course, but like I'm thinking about
for
building
training.
this, like the things that we have seen today.
Right.
How many people have built it and maintain it?
Two, yeah.
You're looking at them. I'm afraid that's all we have time for. Thank you, everybody. Thank you for the presentation,
everyone.
Lanting and Robert.